tree diagram is one of the most intuitive tools to organize all possible outcomes of an experiment. It starts from a single point and branches out for each possible result. This is especially useful when you have multiple stages in an experiment, for example, tossing a coin several times or making sequential choices. Imagine a family with 3 children. Each child could be a boy or a girl. Using a tree diagram, we can visualize every possible outcome. We may have 3 boys, 2 boys and 1 girl. We may have 2 girls and 1 boy, or even 3 girls. So each branch represents one child's possible gender, and each path from start to end shows one outcome. Since one child's gender has 50% chance, all 8 outcomes are equally likely. That's the power of visualization. It makes probability patterns clear. Here we can see that the probability of getting 3 boys is 1/8. Probability of getting 2 girls and 1 boy, 1/8. Probability of getting 3 girls, also 1/8. So we basically can see that each outcome will have equal chance. Imagine you are at a carnival. A game asks you to pick a door and then a curtain behind the door. There are 3 doors and 4 curtains behind each door. By using a tree diagram, we can see there are 12 possible outcomes. Each combination of door and curtain is a unique result. So we can see that the probability of getting the first door with curtain A will be the product of the 2 probabilities, and finally the probability of this outcome is 1/12. Now let's explore a new idea, what we call an event. An event is a subset of the sample space. It's a specific outcome or a group of outcomes that we care about. Events can be simple or compound. A simple event includes only one outcome, for example, rolling a 6 on a die. A compound event includes several outcomes, for example, rolling at odd number 1, 3, or 5. Now that we know what events are, we can visualize how they relate using another tool, the Venn diagram. Venn diagram is a tool to represent relationships between events. They were developed by John Venn and are widely used in probability theory. The criteria of Venn diagram is where it has a sample space represented by a triangle, and then the events are represented by regions within rectangle, usually by circle or parts of circle. Venn diagram can be used to indicate special relationship among events. This symbol represents the union of 2 events, and this would correspond to A or B, which means event A or event B. Meanwhile, this symbol here represents intersection of 2 events, and this would correspond to event A and B. Finally, this symbol here represents the words contained, and this would correspond to event A is contained in event B. The rectangle shows the entire sample space, while each circle represents an event. So here we have event A, which is represented by the green circle and is surrounded by the rectangle representing the sample space. Meanwhile, the area outside the circle represents the complement of that event. When areas of both circles are selected, as shown in this shadow here, that represent union of both events, in this case, union of events A and B. Meanwhile, when two circles overlap, that area represents the intersection, outcomes that belong to both events. Here there is a circle A, which is inside the circle B, which means that event A is contained in B. Now let's take a closer look at this image. Two circles A and B do not overlap. This setup illustrates mutually exclusive event. When two events are mutually exclusive, it means they cannot occur together. If event A happens, event B cannot, and vice versa. For example, when rolling a die, getting an even number and getting an odd number are mutually exclusive. You can only get one outcome per row. Now that we understand mutually exclusivity, let's apply this knowledge to a real-world situation where multiple overlaps occur. In other words, when events are not mutually exclusive. Here is an example where events overlap. The case of students taking multiple science subjects. The school has 63 students studying physics, chemistry, and biology. Out of this, 33 students study physics, 25 students study chemistry, and 26 students study biology. Subject combinations: 10 students study both physics and chemistry, 9 students study biology and chemistry, meanwhile 8 students study physics and biology. Finally, we are told that the number of students who study all three subjects is the same as those who study none of the three. Now let's visualize the completed diagram with all the regions labeled to see the full picture clearly. Here we have the completed Venn diagram displaying all the categories of students and how they overlap. Each section of the diagram represents a unique combination of subjects. Some students study only one subject, others study two, and a few study all three. Venn diagrams is important in probability and statistics because they help us see relationships that would otherwise be hidden in tables or numbers.